Hello students, welcome back to this lecture series. In the last some classes we discussed about the complex numbers and the spacer functions. In this lecture we are going to discuss about the Fourier series. This Fourier is name of the one mathematicians. Okay, that when we are trying to solve the problem in heat conductions, he need to expand functions in the infinite functions expand into the infinite series. Okay, so that time they invent for this series. Okay, so this Fourier series is applicable for the both functions if the functions is continuous and discontinued. Okay, in the last classes we discussed about the Taylor series. So Taylor series we expand for the only continuous functions. If the functions and its derivative is continuous, then we expand the functions in the term of the power of the x by using the Maclaurin series. Okay, but if the function is continuous and the discontinuity of its derivatives, then we can apply this Fourier series. Okay, but the functions must be if the functions f of x is periodic and it's continuous and discontinuous, then we apply this Fourier series. The f of x, we can say if this f of x is a periodic, okay, when the this repeat itself at equal intervals, okay, then we can say this f of x is a periodic functions. Okay, so example of this periodic functions, that is sin x, cos x, okay, with the period 2 pi. Okay, so this f of x, if repeat itself like f of x is equal to f of x plus t is equal to f of x plus 2t and so on. Okay, so t is period of these functions, okay, that repeat itself at equal intervals, that is t. Now sin x and the cos x, okay, and the cosec, these are the example of these periodic functions with the period, this repeats itself with the period 2 pi. Okay, so this is about this periodic functions. Now if okay, now the mathematical form of the Fourier series, that is f of x is equal to a naught by 2 plus summations over n is equal to 1 to infinity a n cos nx plus summations over n is equal to 1 to infinity b n sin nx. Okay, this is a form or expressions of the Fourier series. Now also we can write or if we determine the f of a naught, a n and b n, and that formula is known as the Euler formula. Okay, so this if the function is continuous and discontinuous, so we can apply the Fourier series with this conditions, and that conditions is known as the Dirichlet conditions. Okay, so this if okay, conditions. So conditions is first condition, that is the functions must be single value. Okay, single value functions. Second condition, that is functions must be bounded. Okay. Third conditions, that is has most finite number of maxima and minima. Okay, and the fourth condition, that is has one finite number of discontinuity. Okay, so these are the some conditions. If the function is discontinuity, then if this condition followed by the functions, then we can apply the Fourier series. Okay, this has the most finite number of maxima and minima in the intervals. Okay, so they give the intervals, that is a to b, like so a to b there is a finite number of maxima and the minima, and the same things in the interval has one finite number of discontinuity. Okay, so in the interval, if the finite number of discontinuity, then we can apply this Fourier series for the functions. Okay, and the functions must be bounded, like the sin x, cos x, these are the bounded functions. Okay, so these are the about the Dirichlet conditions. Now, okay, if we determine the a node, an and the bn, these are the coefficients of the Fourier series. So for the a node, we need to just integrate these expressions with the limits 0 to 2 pi. Okay, the both sides. So if it is 0 to 2 pi, if I integrate f of x dx for this side is equal to integrations over 0 to 2 pi a node by 2 dx plus integration over 0 to 2 pi an cos nx dx plus integrations over 0 to 2 pi bn sin nx dx. Okay, so we just integrate these expressions, okay, between this interval, that is 0 to 2 pi. Now if I integrate these things, so it is equal to 0, and this thing is also is equal to 0. Okay, so we have only a node by 2 integration 0 to 2 pi. Okay, so it is a node into pi. Okay, so here a node is equal to 1 by pi integration over 0 to 2 pi f of x dx. Okay, okay, this is the expression for the a node. A node is equal to 1 by pi integration over 0 to 2 pi f of x dx. Okay, now a node is equal to 1 by pi integration over 0 to 2 pi f of x dx. Okay, now if we want an, okay, then we need to multiply these expressions by the cos nx both side and then integrate over the same limit. Okay, so if I multiply both side by the cos nx, so it is integrations over 0 to 2 pi multiply and then integrate. So okay, so 0 to 2 pi f of x into cos nx dx. Okay, this is a multiplication of the cos nx and the integration over the 0 to 2 pi is equal to a node by 2 integration over 0 to 2 pi cos nx dx plus integrations over 0 to 2 pi an cos square nx dx plus this cos square because of the multiplications of the cos nx. Okay, integration over 0 to 2 pi bn sin nx into cos nx dx. Okay, so if we integrate these things, so it is equal to 0, and this cos square nx, if we put the 1 plus cos 2 nx by 2 and then we integrate, so here we get something value, but this thing is equal to 0 and this thing is equal to 0. Okay, so this is equal to 0 and this is also is equal to 0, and for this, so two terms if it's 0, so we have the only one term, that is 0 to 2 pi an into cos square nx dx. Okay, now we replace this cos square nx with the 1 plus cos 2 nx by 2. Okay, so here we get an by 2 Okay, integration over 0 to 2 pi 1 plus cos 2 nx into dx. Okay, and the cos 2 nx, if I integrate, so it is sin 2 nx by the 2n. Okay, if we consider the n, so this is like this: an divided by 2 into x plus (0 to 2 pi). Okay, integration of this thing. So if I put here x, we replace with the 2 pi, so it is 0, and the if I put the 0, so that also it is 0. So both upper and the lower limit, this sin 2x sin 2 pi, that is if we multiply, so 4 pi, so this 4 pi is equal to 0, and the sin 0 is also 0. So for the both limit, upper and the lower limit, this sin is a 0. Okay, so this term is totally 0. So we have an divided by 2. If I put here, so it is 2 pi 0. Okay, and this thing is equal to an into pi. Okay, so here we get the value, that is an into pi. Okay, so an into pi is equal to integration over 0 to 2 pi f of x into cos nx dx. Okay, so we can write an is equal to 1 by pi integration over 0 to 2 pi f of x into cos nx dx. Okay, so this is value for the an. Okay, now for the if we want a bn, okay, so for that we need to multiply these expressions with the sin nx. Okay, so if I multiply sin nx and then integrate over the limit, that is 0 to 2 pi, so it is 0 to 2 pi f of x into sin nx dx is equal to, okay, so integrations a naught by 2 integration over 0 to 2 pi sin nx dx plus an integration over 0 to 2 pi cos nx into sin nx dx plus integration over 0 to 2 pi bn sin square nx dx. Okay, so here this term is equal to 0 and this is also 0. Okay, if this two term is 0, then we have only this one term. Okay, if we integrate, okay, so it is very simple. So here bn into pi. Okay, if we integrate the sin square nx, okay, so then we get the only pi. So here bn is equal to 1 by pi integration over 0 to 2 pi f of x into sin nx dx. Okay, so this is Fourier coefficient, that is a naught, an and the bn. Okay, so a naught, an and the bn's. Okay, these are the Fourier constants. Okay, so let's stop here. We'll discuss in the next class.